In this example, we are going to have butane in a piston cylinder assembly. It's going to undergo isothermal compression at a temperature of 173 degrees Celsius from a pressure P1, which is equal to 1.9 megapascal, to a pressure P2, which is equal to 2.5 megapascal. We're going to find work in kilojoules per kilogram, and we're going to use compressibility data to solve this problem. Now, before we get started, let's go through here, look for keywords. We got a piston cylinder assembly. That's telling us we have a closed system probably. Butane is our substance. We've got isothermal compression. Isothermal, we need to know what that is. We'll talk about it in just a second. We've got our temperature. We've got our two pressures here. And we want to find work. Notice the units, kilojoules per kilogram. And it tells us to use compressibility data to solve. Now, first things first here. What does isothermal mean? What do y'all think that's telling us? Think about what an isobar was. That was constant pressure. And isothermal then would probably be where the temperature stays constant. Okay, so that's what isothermal is telling us. Let's write that down. So T is going to be constant. If you remember when we did those PV diagrams, we had the isotherm where the temperature was constant on that line. So here's an isothermal compression. So T is constant. Now, next thing we want to do, we've got this temperature in Celsius. We can't use Celsius in any of our equations. We need to convert that. So let's go ahead and convert that over. That gives you 446 Kelvin. And let's go ahead and get rid of these megapascals. That's not typically what we want. We usually want to use bar in the equation. That tends to be a little easier. So 1.9 megapascal, that is equivalent to 19 bar. And then for P2, we got 2.5 megapascal. That's equivalent to 25 bar. Now that took care of the little tedious things we had to deal with. Now let's go ahead and get to solving the problem. We want to find work. Now remember we have the work equation that we used back in chapter 2 for piston cylinder assemblies. That was the integral of pressure times your change in volume. We're going to go back to this equation. Now notice it wants work in kilojoules per kilogram. If we have it written like this, work's going to be in kilojoules. So we want kilojoules per kilogram. So in order to make that happen, we're going to kind of restructure this equation. Instead of using regular volume, let's use the fact that specific volume is volume per mass. And then what we can do is we can rewrite this expression as W over M equals the integral of pressure times the change in specific volume now. This gives kilojoules per kilogram. Now, that's the one we'll use. So hang on to that. We'll get back to that equation in just a second. What we want to do now is we have to worry about this pressure. Let's focus on getting that pressure. We can get our pressure P in terms of V using compressibility. And can you think about why that is? If you think back to what that capital Z was equal to, remember Z was equal to PV over RT, right? So let's restructure this equation, solve for P. P, which is pressure, is going to be Z times RT over V. Now in order to do this, we have to know what Z is. We need Z, and to find Z, that means we need reduced temperature and reduced pressure. We got to find these two values before we can do anything else. Let's go ahead and find those. Reduced temperature was T over the critical temperature. And we've got butane. The critical temperature for butane, which you'll find in the table, is 425 kelvins. The temperature here is going to be 446. So we get 1.05 for the reduced temperature. Reduced pressure. For this one, we've got two of them because we have P1 and P2. So let's find the first one. This is going to be pressure over the critical pressure. P1 is going to be 19 bar. Critical pressure of butane in the table, if you look it up, you get 38 bar. That gives you 0.5. Do the same thing for state 2. That pressure is 25 bar, put it over 38 bar. And here you'll get 0.66. Now, using these values, you can go ahead and go to your compressibility chart. Our pressure here is low, it's less than 1, so you're going to go to the compressibility chart that has a reduced pressure ranging from 0 to 1. So for the Moran book, that's figure A1. So let's look at that, and then if you do that, you're going to get 0.84. So let me pull out the table again, and we'll look at why that is. And this is going to be for the first state. So for the first state, we got 0.5 for our pressure, reduced temperature is 1.05. So again, you just come on here, find your 0.5, and then we need a reduced temperature of 1.05, so that's right here. So you come up along this line and you end up meeting up right here at this point. So then you work your way over, and I estimated that to be 0.84. And let's put that that's from figure A1. And then you'll do the same thing for the second pressure, the second state. So we'll call that Z2, and that one's going to approximately be 0.78, and again, that was from figure A1. Now we've got that. We've got our Z values, we've got this equation, and we've got this equation for pressure. So let's combine everything together. So starting, let's call this equation 1. So from equation 1, we know W over M is going to be the integral from state 1 to state 2 of the pressure. Pressure is going to be this equation here. So we got ZRT over V dV. And now when you integrate, let's look. Z is going to be a constant, R is a constant, and is temperature constant? Yes, it is, because we had an isothermal compression. So all of these get pulled out. So essentially your integral that you're doing is dV over V. So that's going to give us W over M equals ZRT times the natural log of V2 over V1. Now we've got these specific volumes, and remember, you can use this same equation and solve for V. So we'll put V2 is Z2RT over P2, and V1 is going to be Z1RT over P1. Okay. So now that we have that, let's go ahead and plug these values or these equations in right here. That'll give us W over M equals ZRT times the natural log of Z2 RT over P2 over Z1 RT over P1. Now R and T, those are going to cancel on both of these, so let's get rid of those. Now let's simplify that. So W over M is going to equal Z RT times the natural log of Z2 times P1 over Z1 P2. Okay, this is a 2 up here. It's hard to see it, but that's a 2. Now we've got this expression here. So everything is great. The only thing we really don't have right now is this Z, because this is just a regular Z. It doesn't say it's state 1 or state 2. So what we're going to do here, we're just going to kind of approximate that, and we are going to let that Z for right here just be an average. So we'll just take 0.84 plus 0.78 over 2. So this is the average of Z1 and Z2. So we'll just say it's approximately equal to 0.81. That'll be close enough for our purposes. Okay. Last thing we need is R. R you can find pretty easily. So remember, R is R bar over molecular weight. This is a capital M here. And R bar, that is a constant. It's 8.314. Molecular weight for butane is going to be 58.12. So divide that, you get 0.143 kilojoules per kilogram Kelvin. So we're almost done, which is good because I'm running out of room here. Now we've got everything to plug into our equation. All right, so we're right here on this equation here. Let's label this as equation 2. It's getting kind of complicated here with all this writing in here. So from equation 2, we're going to have W over M equals 0.81, no units on that, times 0.143 kilojoules per kilogram Kelvin. That's from R. Next, we need temperature. We had a constant temperature, remember, and temperature is 446 Kelvin. So plug that in. And then we're left with this natural log term. So for here, you're going to have 0.78 times 1.9 over 0.84 times 2.5. And that's going to give you W over M equal to negative 18 kilojoules per kilogram. All right, we had just enough room there. Now remember, always look at your sign. This is negative, so that means work is being done on the system. So there's some sort of external energy supply that's being done. Okay, got energy transfer to the system through work. Okay, so that's an example of how you can use that compressibility data in case you don't have your steam tables available to you. You can always use the compressibility charts. All right, guys, I'll see you on the next video.